All right, gang. So the last time we talked, we were looking at regressions. So let's just look at our bestiary table again. Now, as you can see here, we have our dependent variable, which can be nominal or continuous, and our independent variable, which can be nominal or continuous. So far, we've talked about ANOVAs, which have continuous dependent variables and nominal independent variables. We've also talked about regression, which have both continuous, dependent, and independent variables. Well, today we're going to move to another test, logistic regression. So, like regression, with a logistic regression, um, we're still hypothesizing that there's a cause and effect relationship between our independent and our dependent variable. But now we're looking at a nominal dependent variable and a continuous independent variable. So let's just remind ourselves about the null hypothesis of a logistic regression. Our null hypothesis is that the slope of the line we fit equals 0. So what does that look like? Well, say we have our independent variable x, which is continuous. Let's say it's between 0 and 500, and it's a continuous variable. And we have our dependent variable. And just for simplicity's sake, I'm going to put that our dependent variable is either yes or no. All right, so our null hypothesis is that the slope of the line equals 0. So how do we put that null hypothesis in words? Well, the null hypothesis is the probability of getting a no answer versus a yes answer does not change as a function of our independent variable, so x. All right, so our null hypothesis is the probability of getting no or yes does not change as a function of our independent variable. So there are actually a lot of really interesting questions that we can ask and answer using logistic regression. So I want to switch up colors. I like using different colors. So one example is, does expression of a gene affect probability of individual getting cancer? All right, so what are our variables in this? Well, our x variable, our independent variable, is continuous, and that is our level of gene expression. And our nominal dependent variable would be what? Got cancer or didn't get cancer? So cancer or no cancer. All right, another example of a really interesting question would be, does percent body fat of hibernating female, so I'm just going to put female bear, affect probability of having one cub or two cubs? So our X variable, our independent variable, which is continuous, would be body fat of the female bear. And our dependent variable, our nominal variable, would be 1 or 2. So as you see, whenever we do logistic regression, we don't have to have yes or no answers. This could be cancer, no cancer, 1 or 2 cubs. So it's really not just a yes or no type question. So what would this one look like? So we'd have percent body fat of mom, and we would have 1 cub or 2 cubs. And that's what our setup would look like. So I'll give you another example just because, logistic regressions actually are very useful in biology because there's a lot of times when we want to look at a yes or no, a survived or died, a got cancer, didn't get cancer, questions like that where we have a nominal dependent variable. So another really cool question, I think, does age of snowshoe hare, oops, pen's going crazy, snowshoe hare determine whether individual is predated? And I mean, this kind of makes sense, right? So just like with a regression, we have to have a biological mechanism because we are assuming that our independent variable is affecting our dependent variable. So the older a snowshoe hare is, most likely the more they've dealt with predators and they know how to elude predators. So this would look something like that, age of our snowshoe hare, and then we could have predated and not predated. Okay, so our age is our independent variable, and predation status, predated or not predated, is our dependent variable. Oops, wrong one. Okay, so like I said, it's very common in biology that we have a nominal dependent variable that we're looking at. Some examples: survived or died. That's a huge one when you're setting up an experiment, right? It's really important to know whether your individuals are surviving or dying, whether it's plants or whether it's animals. Also, diseased or not diseased. Or not diseased. So think about getting a common cold or a flu. Does the probability of getting a cold vary based on someone's age? Eaten or not eaten, so that's predated. Reproductive or not. Dormant or active, if you're talking about an organism that goes through dormancy. And of course, always yes or no, if it's a simple yes or no question. So they're really interesting. These interesting nominal y variables that we want to study are often a function of a continuous x variable. And that's what we're looking at with a logistic regression. So what does it look like if we reject our null hypothesis and say the probability of getting, for example, a no or a yes, or survived or died, does change as a function of x? What would that look like? Well, that could look something like this, where we have our continuous x variable on this axis, and we have our dependent variable on the y-axis, and we'll just put no or yes because it's a simple thing to look at. So we could get something that looked more like this. That's not a very good. Something that looks like that. We could also get a figure that looks more like this, where we start high and go low. So that would be our alternative hypothesis. But like I said, with a logistic regression, we are analyzing a cause and effect relationship, so we need to have some biological mechanism that we're looking at. So let's just write through a little example really quickly. Let's go with the gene expression and cancer example. So my independent variable is level of gene expression, and genes being more expressed as we go to the right. And my dependent variable is cancer or no cancer. All right. And let's say we get a curve something like that. All right, so when we get our output from our statistical test, like always, we look at our p-values to decide how to interpret our test. So we don't just make interpretations without first learning our p-value. If in this case, this theoretical case, we got a p-value less than 0.05, then we can reject our null hypothesis and say that slope does not equal 0. So if that was the case, then we could have a result statement and we could say, oops, the expression of this gene has an effect on whether or not, or just on whether individuals got cancer. And of course we want to have our test statistic and our p-value, but this is theoretical, so we don't know that. So the really important thing is to not get hung up on the fact that we're using certain nominal and dependent variables. You can use all kinds of variables. So say for example we wanted to use our percent body fat of a female bear example. Well, our independent variable would then become percent body fat of mother. And we were asking, does percent body fat determine whether she has 1 cub or 2 cubs? So 1 cub, 2 cubs. We could just as easily ask that question. So don't forget, you can use many very interesting nominal dependent variables. Survived and died, dormant and active, yes or no, predated or not predated. The possibilities are really endless. So I am not going to be doing a graphing video on logistic regression because it gets pretty complicated in Excel. But the next video you're going to watch is going to show you how to run these logistic regression tests in SassJump. So I'll see you then. Thanks.